Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, today we've got a topic that's important for any automation engineer. Here it is. Modbus RTU Master Setup and Troubleshooting. Well, in today's world of high-speed Ethernet and wireless communications, serial communications details can kind of get lost in the shuffle. But it's still an important element of a lot of control applications out there, so it's important information for automation engineers to understand. And today we're going to cover it in detail. Let's dive right in. So my goal for today's video is really to make this sort of a reference point for those of you who are looking to use Modbus RTU in the near future, or maybe you've got a current project using Modbus RTU, because we're going to walk you through the setup process. We're going to give you lots of testing and troubleshooting tips. So really, no matter what the installation, no matter whether you're using a PLC or Horner OCS all-in-one controller, and regardless of what the slave device is, the goal today is to give you lots of good information that you can use in your project. Now, for those of you who specifically are going to be integrating a Control Techniques variable frequency drive with a Horner OCS all-in-one controller, for you guys, we've got some very good information because that's the specific example we'll be using later in the video with our demonstrations today. All right, let's get started. So what is Modbus? Modbus is really the most common protocol available today for interfacing devices from different manufacturers. Okay, it's not the most advanced protocol, but it's the most common. And it has many forms. We've got Modbus over Ethernet, Modbus over radio, called Modbus ASCII, and then there's also Modbus RTU, which is what we're going to be talking about today. And that's Modbus over a twisted pair hardwired network. So how does Modbus work? Well, let's start by talking about the memory structure that Modbus was based on, or the way data is organized in Modbus. All right, now Modbus was based around or modeled around a traditional PLC. Traditional PLCs have digital inputs and outputs and analog inputs and outputs. So Modbus was organized into coils, inputs, input registers, and holding registers. That's the name for each of the four different types of memory used in Modbus. Coils and inputs are Boolean data, where coils can be read or written and inputs can be read only. And then input registers and holding registers are word type data, where input registers are read-only and holding registers are read-write. Now let's talk about Modbus addressing. In traditional 5-digit Modbus addressing, each of the four different memory types has its own unique address range. That keeps it really simple. So if you're looking at a Modbus address of 35,000, you know you're looking at an input register, which is read-only. If you're looking at an address of 3,000, you know it's a coil and it's read-write. The 5-digit addresses are by far the easiest to work with, in my opinion. Unfortunately, not all manufacturers follow that traditional 5-digit scheme. Some manufacturers will number each of the four different memory types the same, 1 to 10,000. So they've got a 1 base start and 10,000 total memory locations within each type. Others will list what's called an offset. In other words, they'll start using 0-based addressing for the same amount of registers or same amount of addresses per memory type. Now you may be wondering how those manufacturers who list all their addresses the same for each of the four different data types, how they expect you to be able to differentiate them. Well, they're counting on the fact that each memory type has a unique function code or series of function codes for reading and writing to them. So in their charts that show the available data available on their device, they will show not only the memory address or memory offset, they'll also show the function codes that you can use to access that data. So with the combination of the function code plus the address or offset will give you the information you need to access the data. Now let's switch gears and start talking about the physical wiring used with Modbus RTU. Now Modbus RTU is RS-485 based. It's also what's called half duplex. That means it uses the same data pair for both transmitting and receiving from every single node on the network. Okay? Now, most manufacturers recommend a total of 3 wires, a twisted pair for the data, and an extra conductor, which could be half of a twisted pair, for common. Why do you need the common? Well, RS-485 devices can be several thousand feet apart, which means they may have a slightly different ground reference. And if that ground reference is different enough, then there will be communication issues due to common mode. So use that extra common conductor. Now let's talk about shielding. In the best case scenario, you would use shielded twisted pair wiring. However, if you're going to use that sort of wiring, you need to be committed to properly grounding the shield. Because if you don't, you're just going to have a big old antenna attracting electrical noise to your data pair. Not good. And we recommend that you ground the shield at 1 point only, at the best earth ground available. And also, another tip, if you happen to be communicating with variable frequency drives or other devices that are electrically noisy, it's usually better to ground the shield away from that noisy device. One of the beauties of Modbus RTU is that it supports multi-drop wiring. In other words, you're not limited to just 2 devices talking on the network. One master can talk to multiple slaves. You might have a master and 31 slaves in theory. And when you wire that network, you just wire everything straight through. Plus to plus, minus to minus, common to common. And when you have shielded wiring, you want to interconnect your shield drains so that you end up with a continuous shield on the entire network, which again is grounded at only 1 point. Now, whether you have 2 devices on your network or 32 devices on your network, you're going to need terminating resistors, 1 at each physical end of the network. And the value of that resistor should be based on the type of wiring you're using. For most RS-485 wiring, that means 120 ohms at each end. If you're using something like Cat5, it could be 100 ohms at each end. Why do you need terminating resistors in the first place? Well, when you have signals traveling down a network, when they get to the end, they kind of bounce back and reflect. And that is noise that you don't want. So the terminating resistors absorb that energy and prevent that from happening. Now, I know some folks will say that depending on the network, etc., you may not need terminating resistors. My advice is use the terminating resistors. Now, there's another set of resistors that can come into play sometimes with RS-485, and that's called biasing resistors. What are those? Those are pull-up and pull-down resistors that are added at one place on the network, and their job is to take spurious signals and pull them up or pull them down so they don't become ones or zeros and screw up the data. Now, my recommendation is don't add biasing to the network unless you know you need it. So leave biasing off until the end after you've done some testing. And if you don't need them, you don't have to use them. Now, the good news is you probably won't have to get out there with your soldering iron because a lot of devices, like the Horner OCS all-in-one controller, have switchable bias resistors that can be turned on from the system menu or some other setting. Okay? So, again, leave those off until you know you need them, and you'll be good to go. Okay, we're now at the portion of our project where we need to look at the specifics on the Modbus RTU slaves that we'll be integrating. And that means at this stage, we need to find out what Modbus addressing scheme is used by this particular manufacturer. Now, if we look in the user's guide and we see Modbus addresses listed that look like what you see on the screen, that means we've got the best possible case. This manufacturer is using traditional 5-digit Modbus addresses, and there's no conversion required. We can just write those addresses down and use them directly. If what we're looking at instead are numbers that look like the following, small numbers that are 1-based, and we also see function codes listed, that tells us we're going to have to build our 5-digit Modbus address by adding an offset. How big an offset do we add? Well, that depends on the function code. So if the function codes listed are associated with holding registers, for instance, then we need to take that register number in the chart and add 40,000 to it to get our 5-digit traditional Modbus address. If it's an input register with a different function code, you'll add 30,000. Similarly, if we're looking at small but zero-based register numbers listed in the documentation, we're going to have to add a slightly larger number to that register in order to build our 5-digit address. So again, if we're looking at function codes associated with a holding register and we're looking at zero-based registers listed in the chart, then we're going to be adding 40,001 to that value to come up with our 5-digit address base. Now that we've figured out the addressing scheme for our particular slave, now we're just going to make a list of all the different Modbus addresses that we want to read and the ones that we want to read-write. Now, if we're lucky, they'll just be listed directly in 5-digit form. Otherwise, we'll build it like we talked about on the previous slides. We've wired up the network, we've figured out the data we're interested in and the 5-digit format. Now it's time to set up the slave device so it can talk on Modbus. Now, every slave is going to be a little bit different, so the setup process is going to be different as well. There is some commonality, however. Each slave must have a unique Modbus address somewhere between 1 and 247, and each slave, along with the master, have to have matching data rates. In other words, they need to be transmitting and receiving using the same baud rate, data bits, parity, and stop bits. Now, normally my recommendation is to use the default settings on the slave, if at all possible, and adapt your master to adjust to the data rate of the slave. That's typically easier to do. Now, in addition to address and data rate, other things need to be set up as well. With some devices, you'll have to actually enable Modbus. There'll be a setting somewhere in the product to do the enabling. Other products have a convenience feature for adding network termination if their device is on the end of the network. Maybe it's just a switch that you throw to add termination to the network. Maybe it's just a jumper that you add if their device is on the end to add that termination. So check out the manual for your slave device to get it set up. Now it's time to configure the Modbus master, and because this is a Horner video, we're going to talk specifically about setting up the Horner controller as a Modbus master. Now you'll need to start by setting the data rate, data bits, parity, etc. in the master to match what you're using on the network. And then you'll need to set up your polling scheme. What's your polling scheme? Well, the Modbus master is going to be continuously polling a series of slaves reading and writing data. Do you want to poll that data every 5 seconds? Do you want to poll it as fast as possible? That's the polling scheme. Also, you'll need to tell the master about the slave devices. Which slave devices from an address standpoint are connected, and what is their Modbus data format. Usually, it's the 5-digit traditional Modbus addresses that we use, but the Horner controllers have the ability to adapt to other formats if necessary. Also, you're going to have to list all the data that needs to be read or written from each slave. Now, when you're setting this up initially, start simple. Start with one device and one piece of data, get that working, and then you can add more data later. Also, if possible, read or write big stretches of registers, consecutive address ranges, instead of picking and choosing a bunch of individual locations that you're interested in. So if you're interested in 40,001, 40,003, and 40,006, just read 40,001 through 40,006 in one read entry instead of having 3 separate entries. It'll be more efficient and much faster in the end. Now, I'm not going to spend a lot of time in the next few slides because I'm going to be doing a live demonstration. But here's the general process we'll use to configure the master. We're going to use Cscape 10 and we're going to go to hardware configuration. We're going to go to the serial port section because Modbus RTU is a serial protocol, and we are going to select Modbus master from the pull-down list, typically from MJ2. Has to be a serial port that supports RS-485. Next, we're going to go in and set the polling parameters and the data rate for the master, along with things like status register and disable variables that we can set for convenience purposes later. Also, we're going to tell the master about each slave that's configured, and for each slave, we're going to give it a name. We're going to enter its Modbus address between 1 and 247. We're going to identify its addressing scheme, usually using the Modbus PLC 5-digit addressing scheme. And then we're going to add status variables and or a disable variable to the list for each slave. Finally, we're going to start adding entries to our Modbus scan list. That's the list of data that needs to be read or written to each slave. Okay. And then as we add an entry to the scan list, we identify which slave it's coming from, what that Modbus register looks like, how many consecutive Modbus registers we're looking at, and whether we're just reading them or whether these are read-write. Okay, and of course, we also have to map those Modbus registers into local variable space. All right, and in the end, we end up with a scan list of all the data we need to read or write for each of the slaves. And again, it's always better to use more consecutive data areas instead of individual data areas, which end up causing your scan list to get pretty large. Now let's talk about our specific demonstration today. So for those of you who are interested in the UNIDRIVE M400 interfacing to a Horner controller, this specific information is for you. For the rest of you, it shows a good example of the process that we just talked about. Okay, for the UNIDRIVE M400, the first step was we had to install an add-on module to support RS-485 Modbus. Not all drives require this, but the UNIDRIVE M400 does. Next, we had to wire it up to our RS-485 network. In our demo, it's just point-to-point, not multi-drop. You can see we did use twisted pair wire for data, as well as an extra conductor for ground. All right, you'll also notice an extra jumper wire on the M400 side for termination. That's how the M400 handles termination. Just add a jumper wire, very convenient. On the OCS side, we have a setting in the system menu to enable termination on the OCS end. So that's easy as well. My next step was to perform a factory reset. That's because I borrowed the drive from my friend Andy Cluck, and I wanted to start with a known set of parameters. And I performed the factory reset from menu 11, parameter 43. So that nomenclature you see there on the screen with the menu number, the dash, and the parameter number, I use that throughout this presentation. Okay, now in terms of the serial parameters, I didn't change any of them, but I did go in and look at them in menu 11. And you can see the baud rate, data bits, etc., along with the Modbus address are all available in menu 11. Next, I set the start-stop method I wanted to use for the drive to the US style. The M400 has a Euro style and a US style start-stop method. I chose the US style in menu 6. I also enabled the Modbus control word in menu 6, parameter 43. This is that step I talked about before, where with some devices, you have to enable Modbus, and I did that here. And then finally, I had to make sure that I was handling safe torque off properly by connecting a switch to STO1 and then going in and verifying the status of this hardware enable, again from menu 6. And I want to thank my friend Jim Hausch, who sent me his handy checklist that he uses when he connects a PLC or a Horner OCS all-in-one controller to the M400. That was very helpful. Thanks, Jim. So how does CT handle Modbus addresses? In my opinion, they do it brilliantly. First of all, they use the traditional 5-digit addresses, which I always prefer. And secondly, the ingenious part is they link all their parameters to Modbus addresses through a 2-digit menu number and a 2-digit parameter number. So my example there on the screen from menu 6 is parameter 06-043. So we take the 2-digit menu number and we pair that with the 2-digit parameter number to build Modbus address 40,643. Brilliant. That makes it super easy to correlate Modbus data and drive parameters. Here's the list of data I accumulated for our demonstration today of the Modbus data we're going to be reading and writing from and to the drive. You can see it listed here. And this includes a status word and a control word, which are bit-mapped registers where each bit has a different meaning. And on this slide here, I'm showing you the details for the status word, which you can freeze frame if you want to study it. And on this slide, I've got the control word details, again, available for a freeze frame. For our demo, we're going to start with showing you how to configure RTU Modbus Master in the Horner all-in-one controllers. Okay, we start from hardware configuration, navigate to serial ports because RTU Modbus is a serial protocol. MJ2 is our RS-485 port. We'll select Modbus Master from the list of available protocols, and we'll start the configuration by pressing the Network button. This is where we adapt our data transmission parameters, baud rate, etc., to whatever the slave is expecting. Okay, I always recommend you adapt the master to the slave. All right, so we're doing that here with 19200 N82 in terms of stop bits. All right, we also set our timeout values. Really, for a RS-485 network, there's no reason to have a timeout above a second, so I've got mine set to about half a second here. We set our number of retries, how many times we will retry to talk to a particular slave. And then if that slave goes offline because it has not replied to us, for instance, how long will we wait before we try and talk to it again with another 3 tries? And that's the reacquire time. Now, the reacquire time could be set to a higher value if you've got a lot of slaves on the network, but there are really better ways of handling that, so I usually keep the reacquire time low. A couple of other things. You have a bit variable that you can assign that will disable Modbus altogether when that value is a 1. That can sometimes be useful. I went ahead and allocated it here. Also, very important, you have a block of 4 double word status registers available to you. I highly recommend you take advantage of that. We'll give you the details on that later. This is the status for the Modbus Master. Okay, now from setting up the pull rate, which I talked about before, if you just want to pull the slaves as fast as possible, you set your update interval to 0. It'll then pull them as fast as possible. If you want a fixed scan rate, say of 5 seconds or something, then you can set this to say 5,000 milliseconds. But most of the time, most people leave this at 0, so it will pull the slaves as fast as possible. All right, that's the first level of configuration. On the next level, we need to tell the master about all the different slaves it's connected to. For my example, that's just 1 slave, and here's the information. The important information is what is the ID of the slave, and then also what is the format for the Modbus data that it's presenting. Now, nearly all the time, you'll select Modicon PLC 5-digit addressing. The Horner OCS all-in-one controllers can support some other types for some other cases as well, but for the sake of today's discussion, let's keep it at Modbus 5-digit addressing. Okay, we'll leave everything else at defaults. And then a couple more things. Just like with the master, there is a status variable you can assign here. In this case, it's 2 consecutive 16-bit words. I highly recommend you take advantage of that. We'll tell you what it means later on in our video. And then finally, there is a disable bit that you can assign to each slave so you can disable just that slave from being polled. That's very, very useful if you have a network with multiple slaves. Because if a slave goes down, let's say it's offline for a few weeks for maintenance or something, you have the ability to set this bit, which prevents the Modbus master from wasting its time trying to talk to that slave, which is going to be offline for a long time. So if you've got a network with more than just 1 slave, I would highly recommend you take advantage of the disable variable. Okay, after we've told the master about all the different slaves that are available or that it will be talking to, next we start building our scan list. And our scan list is a list of all the data that we're going to be reading or writing from the different slaves. So let's take a look at the first entry that I've previously added to my scan list. Here we present the slave that we're going to be talking to. In this case, it's device 1. We've only got 1 slave in this case. If we had multiple slaves, We could pull them off the list. There would be more than one listed. What is the Modbus register we're going to be reading or writing? How many consecutive registers is that? And what variable or variable array are we going to be reading that data into or writing that data out from? Okay. And then what type of operation is this? Are we just reading the data from Modbus into our local variable? Are we read-writing it? In other words, are we reading the data on a normal basis and occasionally writing it if it changes on the OCS side? And then there's also a variation of that where on power up, the OCS will write its value to the slave and then go about its normal polling routine. And then of course, you can also have triggered reads and writes that aren't part of the poll list, but only occur when you have a trigger bit that gets turned on in your logic. If you have a triggered read or write, then you'll have to assign a trigger bit. Now for most applications, plain read and read writes work fine. The poll list isn't too large. Everything works fine. If you've got an especially large list of data that you need to read or write, for some of them, you might want to make them triggered so that they aren't regularly part of the poll list. That will help you keep your scan rate down. So if there's data you don't really care about getting frequent updates on, you can trigger it once a minute or once every few minutes to get a copy of the data. Okay, so that is building your scan list. Now, one other scan item I want to look at, and that is this one here. This is a polled read where we are reading 4 consecutive registers. So not just 4501, but 4501 through 4504. And this is very efficient to have blocks of data that you're reading or writing. And again, since it's a block of data, we have to read it into an array variable, not just a plain variable. Okay, so that's the scan list. So that is the 4 different levels of configuration, or the 3 different levels of configuration that we need to do to set up the RTU master. Now specifically, for the CT M400 drive demo that I'm doing today, I've got some ladder logic to review with you quickly. Okay, so this is a special routine that I named CT that is basically handling the Modbus data in and out and mapping it over to variables and doing some other housekeeping. Okay, here at the top, one of the words of data that I read in over Modbus from the drive is status information, the status word. I showed you that as a screenshot. And I've copied 3 of the bits that I'm interested in over to local variables, a health variable, an active variable, etc. Okay. Next, I've taken 4 more words that I've received in over Modbus and copied them over to variables for the actual frequency, the actual voltage, the actual kilowatts, that sort of thing. And then in terms of control bits going out for controlling the drive, I've taken local variables, okay, for drive enable, reverse forward, run, those sort of things, and map them to specific bits inside the control word, which the OCS is writing out to the drive over Modbus when necessary, okay, when control needs to happen, of course. And then finally down here, I have a few rungs of logic where I've built a Modbus OK bit, okay? And this Modbus OK bit will let my logic know that all the communications is fine. How does it derive that? Well, it uses that status information available from the Modbus master to determine everything is working properly, and then sets a local bit that I can use throughout my program, including as an LED indicator on the screen. Finally, let's take a look at some of the screens that I've created that tie some of these variables that are being read or written out over Modbus and allow me to control the drive. Okay, let's start with some of the data coming back from the drive itself. These are those 4 consecutive words that I showed you with the actual frequency, RPM, kilowatts, and volts. So this is all read-only data coming back from the drive. Okay, these are all bits that are part of the control word. So I can start and stop the drive. I can switch between manual and automatic mode. Manual mode being where the OCS all-in-one controller is not controlling the drive. Enabling and disabling the drive, changing direction, using the frequency reference from the all-in-one controller instead of the local drive. Could be a analog signal or something that's also wired into the drive, or it could be this reference here that I can set from the OCS. Here's that Modbus OK bit that I derived that I just talked about. And of course, we have a run indicator as well. Okay, so these again are mostly bits from the control word with some status information as well. Now on another screen, I've actually taken the status bits and shown them all here on the screen, along with the control bits that I'm interested in. Okay, and then here is that Modbus RTU master status that I talked about that's so important. And down here is the slave status that's important. And again, this is all really important information, and you really need to take advantage of it. And then as a word in hex format, I went ahead and copied the status and the control words here as well. Again, these are specifically, this data over here is specifically for the CT demo. This is good practice regardless of what slave you're talking to. Okay, let's go ahead and operate the demo on the bench. Okay, so here are those operators that are, for the most part, that are tied to the control word, different bits within the control word. We've also got a word which is the speed reference that we can write down to the drive. We've got our Modbus OK indicator, which is green. Everything is good. Okay, so if I switch from manual mode into auto mode, which means the OCS is in control, you'll see I got an inhibit message on my drive. That's because the OCS has not turned on its enable bit, which I will do so now. Okay, and now our drive switches to ready. And now basically we're ready to operate. So right now I'm going to turn on the frequency reference switch, which basically says we're going to use this speed instead of a different speed reference. We'll use the one here from the OCS, and then I'll hit start. All right, and then you can see we get our actual data filling in here as non-zeros. Our run bit is on as well. Okay, and you can see what's happening on the drive screen. If we take a look at the second page I have here that breaks down the status word and the control word, you can see we've got the individual bits that are on and off there. And then on the right, you can see that we're currently running at about 130 or 150 milliseconds pull rate to read and write the data. Of course, right now it's all reading data, and we're getting strictly good responses. So that's what we want. And then also both of the words in the slave status are 0. That's good. That means there's no problems in our scan list. Okay, so that's what things look like here from the bench with our demo of the CT M400 UNIDRIVE. All right, let's finish up with some quick installation and troubleshooting tips. First of all, keep your network limits at 32 nodes or fewer and 4,000 feet or shorter on your network. There are ways to go beyond that, but in general, those are the accepted limits for Modbus RTU. Also, use good cable. Use twisted pair cabling, where 2 twisted pairs or 1.5 twisted pairs is ideal. I didn't even know 1.5 twisted pairs was available until I saw that recently. Also, if you're going to use shielding, be committed to grounding the shield properly. Have a single ground point on a continuous overall shield for your network, and usually that ground point is where you have the best ground, and it's usually away from noisy components. Also, I know some people will tell you differently, but terminate your network. It'll save you a lot of headaches. Install physical resistors where you need them, or take advantage of switches or system menu settings or whatever is built into the slave or the master to support the termination. Use termination. When it comes to biasing, only use it if you need it. Start with your biasing disabled. If everything's working fine, you don't need to enable it. If you're having some troubles, adding biasing is one of the things you can do to see if that corrects your issue. Also, as I've mentioned multiple times, use the default settings in the slave when you can. match your baud rate, parity, etc. in the master to match the slave. Why change all the slave settings if you don't need to? Also, if you're building a larger network, start simple. Test a smaller network first, maybe only 2 nodes. Once that's working, add nodes and take it from there. When it comes to your scan list or the data that you're reading and writing, do the same thing. Start with a small scan list with just a small amount of data. After that works, expand from there. Use your status registers. There's lots of good information in there. In the master, the status registers will tell you how many good responses you've had from slaves, how many bad responses, how many no responses. They'll tell you how long it's taking you to get through your scan list of data, or if you're working on a fixed pull rate, it'll tell you how many times that you've exceeded that pull rate. On the slave side of things, the status registers tell you if you have any problems in your scan list. This is especially important if you're not 100% sure that the information you glean from the slave's documentation was correct. So if you have a problem in your scan list, this will tell you. It'll also tell you the nature of the problem. Important information if you're having issues. Okay, that does it for our content for today. Remember, we have training available in the 4th quarter, so plan ahead and sign up today. Lots of opportunity to meet us at a trade show out in the field. During the 3rd quarter, we're going to be all over the Midwest and the South. Come check us out. Lots of ways to interact with Horner online on our website at hornerautomation.com, on our YouTube channel, as well as LinkedIn. Next week, we're going to be exploring a network called OSI. So it's really the first time we've covered it on this channel, and I'm excited to do so. So come learn about OSI next week. If you haven't subscribed to our channel yet, don't hesitate to do so. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so until next week when we explore OSI, let's all get out there and do some good.